Yeah, we have a quick announcement before we get started here.
I just want to say that there will be a conference proceedings or a program proceedings. This will be part of the Fields Institute has a communications series, and it will be a part of that. We would very much welcome a contribution from anyone who wants to make it. And there will be a more formal announcement at some point soon. And yeah, if you're interested and you have questions, please get in touch with any one of the organizers and we'll be happy to answer.
Okay, so we have two half-hour talks to finish off our day. And the first one is by Sebastian Chenery, who's going to tell us about gyration stability for projective planes.
Very good. So yes, I should thank the organizers first for the opportunity to speak, and then I should say something about Fred. So I don't have any stories from 1989, but I did meet Fred, and it was in fact the first time I visited Fields. This program from several years ago has been mentioned twice today already, this polyhedral products thing, nearly 6 years ago now. And I remember in particular the talk that he gave, and he was sat there doing some slides, which was superb. But rather than laboring the point, I'll just simply say this and sum up my feelings about Fred, which is, I think it's one of the great burdens of youth that I had less time to talk to Fred about mathematics. So with that being said, on with the talk. So everything I'm going to say, well, most of everything I'm going to say is joint with Stephen. There are maybe one or two places where it's different. I'll make that clear. Yeah, so we start with the ingredients. What do I need to gyrate? Well, what are you gyrating? A manifold. It needs to be, what are the adjectives? Closed, oriented, simply connected. It's an N manifold. Second thing is you need an integer, k at least 2. I suppose really n ought to be at least 3 for what I'm going to say. But we call k the index. And the third thing is you need a homotopy class which I denote by tau. And this lives in pi k minus 1 of SON. And call that the twisting. For reasons which will become apparent. Oh, right. Just before I go on, if you think of M for a second as a CW complex, there's a homotopy cofibration where, if you like, M overline, M bar, is the n-1 skeleton of M, right? Or put another way, if I have the manifold M and I puncture it, that puncture will have the homotopy type of this guy. And I attach the N cell, single N cell, because it's simply connected by some F subscript M, okay? From the twisting tau, construct a map T from a product of spheres to itself, Sm-1 cross Sk-1. Right. And you send A comma X goes to, well, okay. We remember that SON acts on Sn-1. So I take tau of the second coordinate and I act on that by A and leave the second coordinate alone in the image. And this is, I guess secretly tau is a homotopy class, but this is a well-defined map. And with this, we are now ready to say what a gyration is. The K gyration of M by tau is defined by the strict push out, which goes like this. Along the top, I map into Sm-1 cross a K disk, and that's just the identity cross the inclusion of the boundary. And down here, I map into this product, skeleton of M cross Sk-1, and I do this, I perform the twisting, and then I compose with the attaching map for the top cell of M on one side and the identity on the other. The push out of this is written calligraphic G sub tau upper K of M. And that's your gyration, okay? Let's give this diagram a name. Call it star. Some facts. The gyration is an n plus k minus 1 manifold with orientation inherited from M. I think we can believe this because the twisting is coming from SON, and that's orientation preserving, guys. Okay, fine. Second fact. I don't want to say this. It's another way to see it, what a gyration is, I mean. The gyration is obtained from K minus 1 comma N type surgery on the sphere, on the product M cross K minus 1. Okay? And an example. What happens if I gyrate a sphere? And when I put a 0 subscript, that means I'm taking the trivial homotopy class in here, okay? What's the trivial gyration of a sphere? This has the homotopy type of Sm plus K minus 1. Very good. Now, briefly, some places where gyrations come up, so we can sort of motivate the study a bit more. One place is classifying manifolds that admit circle actions. In particular, I want to mention work of Duan from a short time ago. Second place is thinking about four-dimensional manifolds via some index 2 gyration of a 3-manifold. You know, maybe I stand a better chance of trying to understand this complicated 4-manifold if I know it arises as a gyration. And I'll mention, yeah, a paper here. This is Kasperovsky, Donald Chenery, Marcus Land, Mark Powell, and Peter Teichner. 2017. Very good. And the third place that I will mention, and this is where the link to Fred's work comes, is to do with moment angle manifolds. And the thing to mention here is a paper by Sam Gittler and Lopez de Madrano, 2013. Okay. So I've told you what a gyration is, and I've told you why we should care. Now I'll tell you what gyration stability is. So the central question of this talk is the following. Given your index, for which m do we have for which m do I always get the same homotopy type, no matter what twisting I picked? Fun question. But a variation on this question the second. Given your index k and some manifold, how many different homotopy types can your gyration take as we vary the twisting? And the answer to the first question is yes, if and only if the answer to the second question is 1. Yeah? And I guess if I was Fred, I would say that's from Euclid, because it's Euclid's first axiom. But if instead of equal, you say homotopy equivalent. So things that are homotopy equivalent to the same thing are homotopy equivalent to each other. Okay, very good. Let's do some examples of gyration stability. No, I'll keep the ingredients up. Eraser. Examples. What happens if I gyrate the sphere product? Spheres are an easy case. In fact, I sort of lied to you here. This is true for all tau, no matter what twisting I pick. So spheres are duration stable, but this guy has the homotopy type of and as I mentioned something like about this at the start, this was part of a larger piece of work that went up on the archive earlier this year. Now, that's all well and good, but I left the ingredients up here for a reason. Of course, things would be gyration stable if I only had one twisting to pick, like if this group was trivial, right? So K is such that well, if I restrict to K less or equal to n minus 1, then I can invoke block periodicity, right? So this will imply K is congruent to 3, 5, 6, or 7 modulo 8. Fine. And the third example, which is really a motivating example for us, is let's think about a 2 gyration. So I'm declaring that my index K is 2 of a hyperbolic projective plane. This guy's dimension 8. Pi 1 of SO8 is Z mod 2. So I can gyrate trivially or non-trivially, right? So let me write it like this. These guys are known to not be diffeomorphic. And this is this paper of Duan that I mentioned already. So one of the things that we wanted to find out is, are these manifolds homotopy equivalent? They're not diffeomorphic. So let's find out if they're homotopy equivalent. And I'm going to leave that hanging. We'll come back to that. Any questions? Shin has a question at the back. Can someone pass Shin the mic so everyone can hear? Oh, sorry. Yeah, Shin's question. Shin is pointing out that the first example doesn't depend on tau.
Yeah.
Yes, this is true for all tau.
That's
It's an example of gyration stability. Yeah.
Thank you.
Yeah. Sorry, I should have written that. Yeah. Yeah, sorry, that was an oversight. I should have written that. Any other questions? Okay, very good. Very good. Right. Oh, there is a question.
The answer to question 1.
No, if the answer is yes, if the answer, oh, no, hang on. But yeah, if the answer for a given m is yes, yeah, no, you're right. It's a poorly stated question, but I think we understand what I mean, right? Such an m would be gyration stable. Yeah. Yes,
So
this is Lisa's question. Yeah, so Lisa's question is, the answer to question 1 is not yes or no, but rather non-negative integer or infinity. And I suppose, yes, Lisa is correct. Yeah. Yeah. But it's not about the, it's about the manifolds. It's for which m. Anyway, let's press on. We have finite time. I'll do my best to finish with an epsilon or half past. Right. Let's do a bit of homotopy theory. So I'm going to rewrite, no, here. So some of you will have noticed that if I go around this diagram and I follow this sk minus 1, I get a null homotopy because I factor through a disk. Right? So what I want to do is pinch out this disk somehow. Well, how will I do that? I need to tell you about something called a half smash. So if I have two guys, x and y, this symbol, \r times, is going to be x cross y, but I mod out by y across the base point of x. And the important point here is that if x is a co-H space, then this space has the homotopy type of x wedge x smash y. So if I pinch everything out on the right-hand side of these, this vanishes, and I get half smashes here. But it's been rumored that spheres are co-H spaces. So this is really Sn minus 1 wedge S n plus k minus 2. And if I include that larger sphere into here, that fits into another homotopy push out, like so. So really, if I follow the outer rectangle, I've made a homotopy cofibration. Okay, so what have we learned? It goes like this. And the point here is that this is the honest to goodness homotopy cofibration, which attaches the top cell to the gyration. This is the attaching map that's playing the role of this f sub m that I wrote down for a general manifold to begin with. And I'll call it phi sub tau because it ought to depend on the history. Now, let's specialize. Now I need to have time for questions. So I'll tell you what this turns into, then say in words what the strategy is, and then give the theorem. So F here is the complex numbers. It's C, H, or O. We heard a lot about real projective spaces yesterday, but the real numbers don't exist today because RP2 is not simply connected. So respectively, the dimension of M is going to be 4, 8, or 16, right? But the reason this is interesting for us, the reason we can get hold of it, is that this guy will have the homotopy type of SM, where M is going to be 2, 4, or 8, respectively. So we end up with a homotopy cofibration that goes like this. All I've done is apply this to that, where I have a sphere here. Okay, so I was hoping to say more, but I'm running out of time. So I'll just say this in words. If I had 2 gyrations of a projective plane, one by twisting tau and one by twisting, say, omega, right? Then if I could compose phi tau with some self-equivalence of this wedge of spheres, and if that were homotopic to phi sub omega, I would be done. But self-equivalences of a wedge of spheres, here be dragons. It could be more than just the identity on both sides of the wedge. I could have something from this larger sphere hitting that lower sphere that wouldn't show up in homology, but would still be a homotopy equivalence, right? So how does it come out in the wash? I'm going to steal Ulrika's trick. So here I have, these guys are dimension 4, 8, and 16. I'm going up to all indices that are less than n-1, and I'm ignoring the k that come up in my example 2. Okay? Some people in this room have seen this talk before. Ran remembers. Sorry, yes. David has a question. David saw it, yeah. So they will know that this is the audience participation segment of the talk. As I fill in this table, you are permitted to gasp with astonishment. Okay? Very good. So then stay sitting down, Tony. Okay? Sorry, there should have been a health and safety warning at the start of the talk. Right, let's press on. So if I do a 2 gyration of CP2, is it stable? Yes, it is. Ooh, very good. Yeah. How many homotopy types do I get? Well, it's stable, so I have 1. Yeah. So remember, example 3, motivation with 2 gyration of HP2 will be here. Are they homotopy equivalent? No. There are 2 homotopy types. They're distinct, which I suppose is reassuring. But if I do a 4 gyration, it is stable. Hooray. And there's a pattern. Yes, no, yes, no, no, yes. Who was that? You've earned yourself a beer. Well done. 2 But then in this case, something weird happens. I can have 2, 3, or 5 distinct homotopy types. I was going to say more about that, but if you want to know, ask a question at the end. No. But the things get a bit stranger. For 9 and 10, it's 1 on both counts. And here, I have 4, 6, or 10. Now, I'm sure Tony's already noticed, but these numbers are twice these numbers. I'm going to leave that hanging. That's it.
Questions?
Tara has a question.